Right now we're filming because the little numbers are going up. I've got that on film as well. That's immense. The little numbers are going up. Okay, so let's recap these things then. Shall we start with atomic radius? Might have been through all of this before. That's okay, you should be able to do it off the top of your head. So we're always interested in the same two trends. That's the trend across the periodic table, and we usually start from the left and work to the right, which is kind of the Western way of doing things, isn't it? We read from left to right. So we go across the period, sodium to argon, or potassium to whatever that element is over there, krypton. There we go. And then we work down a group as well. Okay, so trend across the periodic table for atomic radius. Cohen, go for it.
They get longer as they go along.
They get longer.
They get larger, sorry.
They do not get larger. Sorry about this. It seems logical, doesn't it? Because lithium has only got 3 protons and 3 electrons, and as we go across, we pack more and more stuff into it. So surely the atoms get bigger. And no, they don't.
They get smaller.
They get smaller.
Is it because the nuclear charge?
Hold that thought. I'll come back to you. Coming down the periodic table, Tom?
Decreases.
It's increase, I'm afraid. 2 for 2. As we go down the periodic table, the atoms do get bigger. Okay. Right. Let's go back to you for going across.
When it goes across, just the nuclear charge increases, so the attraction increases, and it's the same amount of electron shielding, so the atomic radius increases.
So we usually use something like the phrase "no additional shielding," because all the new electrons are going into the same shell. Okay. So we might imagine that sodium's got its 1 electron there, and over here fluorine's got its 1 electron there, and fluorine's got 6 other electrons as well, but they don't get in the way of that electron. So sodium's not fluorine, is it? Chlorine. Come on, wake up. So sodium's over here, it's got 11 protons. Chlorine's over here with 17 protons. So the sodium 1 electron or outer shell electron will experience a less charge than chlorine's outer shell electron, which holds the chlorine electrons more tightly. So we use that term greater attraction, and remember, if we're talking about attraction, there must be 2 things. We're interested in the outer shell electrons and the nucleus. Okay. All right. Going down. So what's changing as we're going down the periodic table?
Increasing shielding.
Can we go back to Tom? What's changing as we're going down the periodic table that makes the atoms get bigger?
Mass to charge ratio decreases.
Yeah, mass is a bit of a red herring. Just focus on the electrons.
There's more shielding.
Because there are more
shells are being filled.
Okay, so
There's a weaker.
more shells and more shielding. I would try and use those 2 together. They kind of come together. More shells, more shielding. They both begin with sh. More shells and more shielding. So Baker attraction between outer shell electrons and the nucleus. Okay. Super duper. How does that change if we think about ionization energy?
The increase.
I was going to ask Paul. First of all, what happens to our two trends, ionization energy? Notice you've got some information now that might help you work it out. So going across the periodic table, how does ionization energy change?
It'd be the same. Like it would
What's the same?
like it would increase as well.
Right, it does increase, but atomic radius decreased. It's not the same.
Oh.
It's the same effect. So I'll come back to those, but
Like
it's a different word I'm writing in orange than I wrote in black.
Nuclear charge.
Yeah, okay. So I'm going down periodic table.
Decrease.
Yeah, they're always opposites. So if you get one right, you get the other one right. Okay. So what? Let's say the question in the exam was, why does ionization energy increase across the periodic table? What part of that would I need to change, if anything?
You just need to add on that more energy is needed.
That's exactly right. Needed to, what are we doing when we're ionizing?
Remove electron.
I'll say an electron because I'm assuming this is the first ionization energy. And then going down groups. Benji, could you fill in a
Less energy is needed.
less energy is needed. So we've got our stock answer in our heads to do with shells and shielding and nuclear charge and attraction and blah blah blah. All we need to do then is adapt that with a little bit of extra information for ionization energy. Electronegativity is not actually on the thing we're doing here, but I'm just going to mention it because it does tie all together nicely. How does electronegativity change going across the periodic table?
Increase.
Yeah, so you probably remember that fluorine right over here in the periodic table has the highest electronegativity. Of course, your group 0 gases don't have an electronegativity value. Why was that?
Full out shell.
Yeah, close, full outer shell, so they don't.
Attract the electrons, bonding electrons.
You don't react.
Yeah, they don't react. They don't form bonds, so they can't attract the bonding electrons, which is what electronegativity is a measure of, because they don't have any bonds. So instead of the line in orange, more energy is needed to remove an electron. That's what we had for ionization energy. What would we suggest for the last line for electronegativity. Do you want to fill that one in for us, Karen?
Yeah, sure.
So replace that orange line there with a new line that we would write if you were explaining why electronegativity increases. Or maybe change something else.
The nuclear charge is greater, so it's got a greater attraction to the bond.
Ah, there we go. So I just have to change that word to bonding, don't I? I don't actually need that last line there at all. And the same here. Okay, if I change that bit to bonding. I know it looks a bit of a mess now, but I'm just trying to illustrate how these two answers are really good for answering 3 different types of question each. We can use the same answer or the same sort of template to talk about ionization energy, electronegativity, or atomic radius. Okay, so let's just stay with ionization energy for the moment. So we've just said the general trend going across the periodic table is for an increase. More energy is needed to remove an electron as we go across. So I'd expect my graph to go up as we go across the periodic table. Well, it's going to go up, but it doesn't go up uniformly. Which 2 elements don't stick with that trend? Which 2 elements kind of stick out when I'm drawing my points? Aluminium and sulfur. Okay, so we normally have something like this, and then aluminium drops a bit, and then silicon and phosphorus, it goes up. Sulfur, it only comes down very slightly, but it definitely comes down, and then goes up for chlorine and argon. So the important ones are sulfur, something weird is happening there, and aluminium, something weird is happening there. So I say something weird is happening. Of course, this would have been the empirical evidence. This would have been the experiment that the scientists would have done in the lab, and they would have been measuring the ionization energy of different elements, and they would have noticed that it goes up from left to right, and that's probably fitting with their hypothesis. But then aluminium and sulfur bucking the trend there, going down, there would have been like a bit of a head scratching moment there. Hang on, what's going on there? What is going on there? So you'll often see this kind of question in the exam. Sorry, why is that's right. Energy, sulfur, phosphorus. I sometimes think in chemistry, one of the reasons that chemistry is hard is that when we look at these two explanations, and indeed the explanation for why ionisation energy goes up as we cross the periodic table, the explanations are they're always about something different. And it's like we're using this explanation for that phenomena, and then we're using a completely different explanation for a different phenomena. And it's how do you know which explanation you're supposed to use for which different thing? Well, you just have to learn it. It's the joy of inorganic chemistry. Right, let's start with aluminium then. What is it that we're looking at? Where do we need to go for evidence here? What's the important bit of information that would help us unscramble this? Help and information is in the topic booklet. Subshells. Okay, perfect. So if I look at magnesium, one way of doing this is just to sort of assume that we've got the 1s2, 2s2, 2p6 stuff is all done, and then we have 3s and the 3p. So for magnesium, we've filled the 3s, and then for aluminium, we've got all the same electrons in the base there, but then we've got one electron in the 3p. Okay. So why does that make a difference? This isn't really relevant to this one down here, but you might have seen this kind of diagram. Okay, these are not just lists, are they? Every shell, every subshell has an energy. So when I'm putting in the electrons for, well, any element, we always fill from the bottom up. For aluminium, we've got an electron in the 3p, but the 3p and the 3s aren't at the same energy. 3p is higher in energy. If we imagine that in order to get the electrons out of the atom, I've got to get them up to some energy up here. If I'm getting an s electron out of the atom, I've got to get it all the way to there. If I'm getting a p electron out of the atom, it's got a shorter distance to go, or less energy. So we can use that idea. So the aluminium outer electron is in the 3p orbital, or the 3p subshell, which is higher in energy. So it's higher in energy, I should have said, than the 3s. If we're using a comparative, we have to be comparing it with something. So higher in energy than the 3s. So less energy is needed to get that electron out of the atom than the 3s. And the further back we go, the deeper the electrons are in the atom. They're actually closer, physically closer to the nucleus, more tightly held. It takes more energy to get them out. So it takes a lot of energy to get a 1s electron out of the atom, compared with, say, a 3s electron, which is why as we go down group 1, they get more reactive. Okay. What about the sulfur thing? Phosphorus. what's the difference between the electron structures of these two guys here? Phosphorus has got 3 electrons in the 3p, so that's the 3s there. That's the 3p again. Sulfur's got 4.
They have like one of them is not like one of the boxes only has one thing in it. You know what I mean? So like
Not quite.
The sulfur electrons are paired, is it?
yeah.
What do I what?
Like they're not paired.
Right. So what would I draw for the electrons for the 3p for phosphorus?
Just one.
How do I draw that?
It'd be like one line in that box and one line in that.
Yeah. So 1 electron in each box, or
Yeah.
boxes are called orbitals. Yeah. So each orbital in the 3p has 1 electron in it. So then when sulfur comes along, it's got 1 more electron because it's the next atom along. So it must have 2 electrons in one of the orbitals. And just like electrons sharing orbitals, it's a bit like siblings sharing bedrooms. Usually find that's a fairly easy analogy for young people to work out. Sharing a bedroom causes some repulsion quite often. And it's the same for 2 electrons sharing an orbital. So it's important you use the language correctly here. So I need to see that word orbital, not shell or subshell. 3p is a subshell. Shell is 3, we're in the 3rd shell. 3p is a subshell, 3s is a subshell. But each box is an orbital. So 2 electrons in the same orbital, which causes repulsion. In other words, the 2 electrons kind of reject one another, and they're very keen to get rid of the other ones. So when the energy comes along, it takes a bit less energy to get that electron out.